You remember that in the last class we had said that we are doing with the Cartesian coordinate, that is x, y, z. Now this time we will be doing with the cylindrical coordinate, that is r, theta, z. Right? With that we will do. So let us look into. So unlike the previous one, where we had said that x, y, z was the coordinate, here we take some cylindrical coordinate like this, and right, and okay. Okay. So this can be del theta, this can be del r, and this is del z, right? So in the coordinate system we have r, theta, z. So this is z, this is theta, and this is r. So if we take r, theta, z coordinate, then here we are taking this point as the r, theta, z coordinate, right? And in the previous one, if you remember, where we had said, let me just recapitulate, where we had said that we were taking a volume element at the center, right? We said if this is going like this and that is going like that, so how much mass is coming here? We took it as the balancing point. So here in this case, if we take this balancing point to be at the r theta z point, right? Then this is of course r plus delta r, this is r plus delta r, this is theta plus del theta, and this is z plus del z. Only one thing which is we are taking, that area under this and area under this, they are, though there is a difference, because in all the cases this will be all difference, and in that case we will take, this is z plus delta z, right, and this also will be different, this also will be r plus del r. So all the changes whatever, since we have said we are taking the volume element very small as possible, so those changes we will be ignoring, otherwise this will become too complicated. So just to avoid the complication, we are assuming that this area under this and the area under this, they are more or less same. So the changes with that del quantity r plus del r, or theta plus del theta, or z plus del z, these we are neglecting for the upper one, right. So if the on the similar fashion as we have done in the Cartesian coordinate, so if we do for the cylindrical coordinate in the same way, then we can write in the face r, right, in the face r, that is m dot r into del r, right, or del a rather, area del a. So which is m dot r into, the area is which one? In the, if this is r, right. So r del theta del z, r del theta del z is the area r del theta del z. So, del z is this, right, and this one will be r plus del r, but this is del theta plus del theta, right. So, the face which is having the area r del theta del z arc is this arc, right. This arc r del theta is that, and we can say that here it is m dot r del theta del z, right. So, now m dot r was what? Rho V r into r del theta del z, right. So, this was in. So, out r or r plus del r. So, out r plus del r is at this point or at this point in this plane, that will be equals to m dot r plus del r at m dot r, right, into the entire del r, right, del r of m dot r into entire del r, right, into the area is r plus del r into del theta into del z, r plus del r del theta del z, right. So, this on simplification we can write that this is nothing but rho V r del theta del z plus rho V r del r del theta del z plus del r of rho V r del r del theta del z, right. So, we can say that in was like that earlier, and in minus out we can write in minus out to be equals to rho V r del theta del z minus rho V r del theta del z, right, minus rho V r del r del theta del z minus del r of rho V r, right, into r del theta del z del r. So, this on simplification gives us minus rho V r del r del theta del z minus del r of rho V r del r del theta del z, right. So, this we can say in the previous class we had said that we expanded in the UV method we expanded rho V, right, keeping V constant, rho we varied, keeping rho constant we varied V. If you remember that del r of rho V r, that how can we expand it. So, here also we can expand it, or we have already expanded form, which if we do the other way, then we can make them as the compact one like this, that this is equals to minus del r of r rho V r into del r del theta del z. How? If we expand this del r of r rho v r, if we expand this and take this rho v r and r as the uv product, right, as the product, both r into rho v r, if we take this as product, then in one case r is constant, right. In one case r is constant, then it is on expansion it is coming r, right. Obviously in both the cases a negative sign is there. So in one case it will be r del r, right, rho v r del r of rho v r del theta del z, right. And in other case this del r of rho v r is differentiated, or rather this is one uv expansion, and the other one, if rho v r is constant, then del r of r is 1. So in that case rho v r del theta del z, that becomes 1. So this is u and this is say v. If we make uv the del of something of uv, that expansion method if we apply here, then that expanded form is like this, which on clubbing we get r rho v r as the variable, and del r of r rho v r del r del theta del z is the in minus out, of course with a negative, right. So similarly we can say for the other two cases that in minus out for this in minus out for r coordinate, we can write that this is nothing but minus del r of r rho v r into del r del theta del z. So in a similar way, exactly in a similar way, we can also write in minus out, that is mass flow in minus mass flow out at the coordinate theta, then we get similar to that. Okay, let us do this way, that in minus out this way, in will be rho v theta r del z, rho v theta r del z, and out will be rho v theta plus del or minus, this is del theta of rho v theta, del theta of rho v theta into del r del z, right. So that means this in minus out we can write to be equals to, so this rho v theta into del r del z, rho v theta into del r del z, this goes out, then we can write this way, that minus del theta of rho v theta, right, rho v theta into del theta del r del z, this is that in minus out, minus del theta of rho v theta del r del z. right? So in was this was for r coordinate. In the theta coordinate, in was rho v theta r del r del z. R del r is the mm, oh, this is 2 del has come, that is why. So r del r into del z, that was for in, and for the out it was rho v theta plus del theta of rho v theta into del r del z, right. So if we remove that, then we can say that this we can write del theta of rho v theta into del theta del r del z is the in minus out at the theta coordinate. Okay. Similarly, for z coordinate, in at the z, we can write rho vz into the area r del theta into del r, and out at the z we can write rho vz plus del z of rho vz, right, del z of rho vz into del z times the area. This area is r del r into del theta, right. So this we can then write in the z coordinate, in minus out at z, this is equals to minus del z of rho vz, right, into r del z del r del theta, right. So by adding in minus out in all the three coordinates, we get in all three coordinates r, theta and z. In all three coordinates, if we add, then in minus out we get minus del r of rho Vr times r rho Vr, right, times the volume del r del theta del z plus del theta of rho v theta times the volume, that is del theta del r del z plus del z of rho vz, right, times r del z del r del theta, right. So this is on adding r, theta, z, all three coordinates, right. Then we have to also find out the accumulation, isn't it? You have to find out the accumulation, and in that case, what is the accumulation? That we have to find out, right. So accumulation is del rho del t in the entire volume element. Volume element is r del r, there is one side, del theta another side, and del z the third side, right. So this r del r is one arc and del theta del z the other two. So this is the total volume. Okay. So if we now put that mass in minus mass out is equal to accumulation, this balance, mass balance if we do, then we can write r del rho del t, that E plus del r of del del r of r rho Vr plus del del theta of rho V theta plus del del z of rho Vz into r, this is equals to 0, right? Because this r del theta del z, r del theta del z, that goes out and we get this. Okay? Then we can write this to be equals to, we can write then this to be equals to del rho del t plus del r of rho v r rho Vr, right, del r of r rho Vr plus del theta of rho v theta, right, plus del z of rho Vz, right. So, this is equals to 0. So, on accumulation we get this del rho del t plus del r of r rho Vr plus del theta of rho v theta plus del z of rho Vz, this is equals to 0, right. So, one thing we have to keep in mind, of course, this r which was there, this r which was there, if we divide all the three terms, then here in the del theta of rho v theta, here we should have 1 by r, isn't it? That should come out there, and that is equals to, because in all the three out of these we had here at 1 r and we had here at 1 r, also we had 1 r here, right. So, in that case this r and this r, if we divide them, then they should be 1 by r del r of r rho Vr, and this should be 1 by r of del theta of rho v theta, and this is like that, right. Now is the real expansion. So, if we see that this is quite little not a little, quite different than that of the xyz or Cartesian coordinate. So, we can write that in the r theta z or cylindrical coordinate, the actual term is del rho del t plus 1 by r del r of r rho Vr plus 1 by r del theta of rho v theta plus del z of rho Vz. This is the equal to 0, is the equation of continuity for the cylindrical coordinate, that is r theta z, right. So, this is quite different than that what we had done for the xyz, that is the Cartesian coordinate. If you remember, that was absolutely different than this. So many additional terms have come. Now, these will be also useful when you are going for the equation of motion, that derivation. These relations will be helpful substituting for expanded or contracted form. So, in that case, there we will be using these relations either in the Cartesian or in the cylindrical coordinate, right. So, we have done both, then xyz, that is the Cartesian coordinate, and r theta z, that is the cylindrical coordinate. These two systems we have shown how to derive the equation of continuity and what is the form of equation of continuity, right. Now, this will not derive, but we can say for the spherical coordinate, we can say that del rho del t, this is del rho del t, this plus del r of r square rho v r square rho v r, right, del r of this into 1 by r square plus 1 by r sin phi if our coordinate system is r theta phi, right. Then we can write like this 1 by r sin phi into del theta of rho v theta sin theta, right, plus 1 by r of sin phi, 1 by r of sin phi del theta of rho v theta, right. So, this is equals to 0 for the r theta phi coordinate, that is spherical coordinate. So, spherical coordinate we are not deriving because r theta phi, that will be too much complicated and will take really good time. And to avoid that, we are giving the final form of the r theta phi, that is spherical coordinate. The final equation is del rho del t plus 1 by r square del r of r square rho v r plus 1 by r sin phi del theta of rho v theta sin theta, right, rho v theta sin theta, and del 1 by r sin phi del theta of rho v, this is okay, this is theta is there. So, if you mix up, this is phi rho v theta, right, rho v phi sin phi del, so r phi theta, then we should write in this form r phi theta, right. Second term we are writing in terms of phi. So, 1 by r sin phi, right, to del phi of rho v phi sin phi plus 1 by r sin phi del theta of rho v theta is the spherical coordinate, right. So, we have already seen that partial coordinate, that partial derivative was del rho del t, partial derivative was del rho del t, then total time derivative, that was d rho dt, and we also had shown that the substantial time derivative was capital D rho dt, right. So, these three and their respective expressions also del rho del t is okay, but d rho dt we had also shown. This will be required next for when you are doing the equation of motion, that time again it will be required. So, d rho dt we had shown that this was del rho del t, right, plus del x of rho or del rho del x into del x del t plus del rho del y into del y del t plus del rho del z into del z del t. This was for the del z del t. This was for the partial derivative, but this was for the total derivative, and for the substantial time derivative we had shown that this was d rho dt. This is equals to del rho del t, right, plus this will be again required Vx del rho del x plus Vy del rho del y plus Vz del rho del z, right. So, this will be recurring when we are going for the equation of motion, that set of equations. We said earlier that this we call very useful equations, Navier-Stokes equation. So, when we do that, all these relations will be very much useful and they are required, right. So, in the next class we will do the equation of motion, keeping in mind that the continuity equation and in the all three coordinates, that is Cartesian coordinate or cylindrical coordinate or spherical coordinate. In all these three coordinates we have, out of those two we have derived and one we have shown you the final form. So, these forms will be utilized for equation of motion. But again, equation of motion, you will see that it is, as we are progressing, it is bigger and bigger. So, equation of motion will be even bigger, right. So, in that case it may not be possible that all the three coordinates will be showing, but at least for the Cartesian coordinate will show. Okay. Thank you.